Good morning, all of you. In today's class, we will start with the Lebec integration or measure integration. Both are one and the same. I think you are already studied the set as well as the functions. These are the two fundamental things whenever we start with the applied calculus. Is it correct? In your PU classes, you may be aware of that in the differentiation. In the differential calculus, or you can start it with the calculus, means you started with the differential calculus first. Then only you studied the integral representation. In previous classes, I already mentioned that the existence of differential calculus comes the next stage. Actually, the integration comes first. You know that whenever we have some lot of money, then we can spend easily. Is it correct? That's why the integration means it is a summation. Differentiation means we can use a decrement of that function. For fundamental structure of studying the differential calculus, we started with the differential calculus first. First started with the function and limits, and after that we studied the continuity, then the differentiability, and so on. After that, we sketch on to a integration. Is it correct? This is the procedure we started in our early career of mathematics in differentiation. Here in the higher order thinking, we always started with the integration first, because you already know the sets and as well as the functions in your hand. Now we will start with the Lebec integration, and you already know the one of the curve structure. That curve structure can be done in a Riemann, the ordinary integration. The sophisticated version is a Riemann integration. You already studied in your UG course. Now, in this class, we will start with the Lebec integration. In this class, we will start with what are the shortcomings of Riemann integration, why we need the Lebec integral, and some of the pictorial representation of a Riemann integration versus the Lebec integral. Whenever here we will use Lebec measure integral or Lebec measure is one and the same. And also we will discuss some of the theorems in the later stage, but I will focus more on how the Riemann integration versus the Lebec integration is useful in this class. Here, the definition of Lebec integral is a parallel to the definition of Riemann integral, except that a Riemann integral we use subdivision of closed interval a comma b into subintervals, while for a Lebec integral we use subdivisions of closed interval a comma b into more such general kind of measurable set. Because we already know the measurable set, then we can extend it to a, you already know the union of measurable sets is measurable. Using that concept, we can extend the Lebec integral. The Riemann integral is based on the fact that by the partitioning the domain assigned function, we approximate the assigned function by piecewise constant function in each subinterval. In contrast to the Lebec integral, partition the range of the function. This is the major difference between Lebec integral and Riemann integral. You can see one of the pictorial representation of Riemann integration versus Lebec integral. You can see here, if you make a Riemann integration here, this is the Lebesgue integral. Here, the less of that part will be not vanished in this Lebesgue integral. This is the general form. Now we will, what is the intuitive interpretation of a Riemann-Darboux integration, or same as Lebesgue-Darboux integration? That is one and the same, because they are mentioning in the their intuitive way, means how we can sketch one of the examples related to Riemann and Lebesgue integral. Here I mentioned here in blue, that is the Riemann integration, and red it is the Lebesgue integral. To get some intuition about the different approaches to integration, let us imagine that we want to find a mountain volume above the sea level. Here, this is the one of the example. The Riemann-Darboux approaches divide the base of the mountain into grid of 1 meter square. This is simple example. It is depending on the how we can calculate. Measure the altitude of the mountain at the center of each, because here we can start center of each square. The volume of a single grid square is approximately 1 meter square. You can see here the square of the altitude. So the total volume is 1 meter square times the sum of the altitudes. This is the Riemann-Darboux approach. Then you can see here many things are, the errors will appear. But the Lebesgue approach, first we can make a contour of the map. You already know the contour map. In a complex analysis, there is you can make a map of the contour of the mountain. This is, we say that it is a contour where the adjacent contours are 1 meter of the altitude apart. The volume of each single contour contains approximately 1 meter that contours area. Whatever we taken, so the total volume of the sum is this area is 1 meter square. Here, very less thing of the very small portion of approximation or errors will appear in the Lebesgue integration. This is the fundamental thing. First, we can start with this. And this is the one of the example. You can, I given one of the web address. If you go to this web page, you can see here how how in the Riemann integration versus Lebesgue integration started with the 5 and up to the 160 level, how it is quickly approaches the final integration part. You can see in the web page, it is there. You can interactive resources in the mathematics. You can see in the calculus part how it is covering quickly in the Riemann integration versus Lebesgue integration. This is the fundamental thing. We can start with the
need the Lebec integral when we already have the Riemann integral. In this video, I explain why we go from the classical integral definition, which is the Riemann integral, to the more modern one, which is the Lebec integral. However, let us first start with the Riemann integral. Here we want to integrate a function f that starts from R and goes into R. So a normal function defined on the real line and with values in the real line. And as you should know, this integral is related to the calculation of an area below a graph. So let me do a rough drawing of this graph for the function f here and consider an interval on the real line. So maybe we start with A and go to B. then we are talking about this area below the graph. So exactly this one. In short, this means the Riemann integral of the function f from the interval ab is related to this area here. Therefore, we have the well-known idea to choose a partition of the x-axis and to approximate this area by choosing rectangles. And this approximation is known as the lower sum or the upper sum. So what I draw here is the well-known lower sum. And if we now choose finer and finer partitions, we call this limit of the lower or upper sums the Riemann integral if the limit is well defined. Well, this was a short summary of the Riemann integral, and now we immediately find some problems here. These problems give us a reason to define another integral notion. Firstly, it is difficult to expand the Riemann integral to higher dimensions. Yes, you can expand it to higher dimensions, so it is possible, but it's very laborious. For example, if we would have a 2 here. This means that the x-axis here is now a two-dimensional space, so we can't use rectangles for the partition. Of course, we now could use cuboids. So if this is the two-dimensional space in the domain of definition, this R2, then our partition is now just rectangles in this plane, and our integral approximation now is given by cuboids. So maybe in this way. As you can see, it gets very technical, and it will be much more work with this additional dimension. It's just one more dimension, but you have to do much more work. For example, to build the limit process in the end. This is directly clear if we consider the domain of definition here. In the one-dimensional case, we only had an interval. So this is an easy thing since it starts with A and ends with B. It's just an interval. But even if we add only one dimension more, so here's the picture, x1, x2 and f of x1, x2. So even if we just add one dimension, there are a lot of more possibilities. For example, the domain of definition for the function could be a circle in this plane. So let us focus on the domain of definition now. So I draw another picture, just the x1 and x2 axis, and then we find the circle just there. What we now want to do is choose a partition of the circle and put the cuboids above. However, of course, this is not exactly possible, so we can put rectangles inside the circle here. But as you can see, we even need a limit process to approximate the circle in the domain of definition. Again, I said it is feasible, but it's a lot more technical work. In summary, this is one problem of the Riemann integral we directly understand. It is much more work to do this in higher dimensions. The second problem of the Riemann integral, and what you should know from this one-dimensional case, is that we need some continuity property for the functions we want to integrate. In other words, we have some dependence on continuity. We call that, in the best case, the function we want to integrate should be continuous. Then we don't have any problems. However, if we have discontinuity points, then there should be only finitely many of them. But if we have infinitely many, it can destroy the integrability of the function. I hope you know the typical example. So an easy function that you can't integrate using the Riemann integral. Hence the dependence here is indeed a disadvantage of the Riemann integral. Now the most important disadvantage of the Riemann integral is the relationship to limit processes. The question is here, in which situations is it allowed to interchange some limit processes? Or in other words, can I pull a limit sign inside the integral sign? So let me show this in an example. So we have the limit n to infinity, and we integrate a function from a to b. So this is a sequence of functions fn, and we integrate them with respect to x. The question is then, when is it allowed to pull or to push the limit inside the integral. So when does this equality hold? For the Riemann integral, we don't have many possibilities here. We always need the uniform convergence of this sequence of functions. Only then we know that it is allowed to pull the limit inside the integral. However, this uniform convergence is a very strong notion and in some sense related to the continuity again. And therefore, we want to weaken this notion. Indeed, we have a lot of examples where there is no uniform convergence of the sequence of functions at all, and we still have the same result on both sides. Hence we know it should be possible to generalize this convergence theorem. However, not by using the Riemann integral. The Riemann integral is just not flexible enough to prove such a convergence theorem. Well, these are three important points that show the difficulties we may have when we use the Riemann integral. Most importantly, we have a wish to the generalization to higher dimensions. So we want an integral notion that is not restricted to one dimension. So we don't want to do all the work again if we just change the space of the domain of definition here. We want an integral that works in every dimension the same. In order to understand this generalization, we need more technical details. Hence, I would suggest we start with the Riemann integral. Again, we do some sketch. So we have the x and the y-axis. We also have a function where I draw the graph in green. So we have a function with values in the real numbers. For the Riemann integral, we now choose a partition of the x-axis as before, and now we can calculate the upper and the lower sum. Here I have drawn the lower sum, which means that we take the infimum in each subinterval for the height of the rectangles. And for the upper sum, we will take the supremum. So here, for example, this rectangle. Hence we get the upper sum. If the difference between the upper and the lower sum can be made arbitrarily small for a finer partition, then we can define the Riemann integral. Then you can define it as the supremum of the lower sums or the infimum of the upper sums. This is then the same value, and this value is called the Riemann integral for the function f in the interval ab. In order to do this, it was necessary that we have a function that goes from the real numbers inside the real numbers. Otherwise we can't do the partition of the x-axis, and we don't have a height here. The idea of the Lebec integral is now different. As you have seen before, it was very restrictive to find a partition of the domain of definition if it is not R itself. So if we, for example, have a three-dimensional space, then we can't find a partition easily. But we map still in the real numbers. So the right-hand side is still the same since we consider functions. So functions with values in the real numbers. So this is the same. The left-hand side is not the same. This means that the domain of definition, the left-hand side here, can be very high-dimensional or even very abstract, and therefore we don't know what a meaningful partition of the left-hand side should be. Just because we don't have these simple intervals in a high-dimensional or abstract space. However, on the right-hand side, we still find the real numbers, the one-dimensional space of the real numbers. So instead of find the partition of the x-axis, it would be easier to just find the partition of the y-axis. And indeed, this is what the Lebesque integral does. Although this is not the way the Lebesque integral is normally introduced. However, it is still a very good idea to visualize the Lebesque integral. So let us draw the graph again. And keep in mind, the x-axis may be high-dimensional or even abstract, but the y-axis is still the real line. And that is what we decompose now. Since this is only the real line, we can find the same interval partition as before. So we choose some values and define some intervals here. So this is a partition of the real line as we did before in the Riemann integral on the x-axis. So maybe we call these partition elements Ci, where we in the Riemann integral we usually denote them by xi. Maybe as a reminder, what we did in the Riemann integral was we defined an upper sum of some partition of the x-axis. So you would write u of the partition, and this is the sum of all the rectangles, which means a sum, and then you choose the supremum inside the interval times the length of this interval, so times the length of your partition, so maybe delta xi. And you can do the same for the lower sum. Then again we sum all the rectangles up, but each one is given by the infimum inside the given interval, infimum of f of x times the length of the rectangle, so times the length of the interval there. So I call it delta xi. In this way we usually define the Riemann integral. However, now we want to decompose the y-axis for getting the Lebesgue integral. Now we get the following picture. For example, this line here, so this value gives you this line here and this line here. Now we want to find all the parts of the function that lie between these two lines, so meaning inside this interval or in the real line. This means that we don't draw rectangles as before, but we look which part of the functions lie inside these two lines. Then we find here that we have one part on the left hand side, so we find all the arguments in x that lie in this set are sent to values inside this interval by the function f. And we also have here a part of the function, so we can project it again down to the x-axis, and then we find, okay, all the arguments in x here are getting sent to the interval. Now these two parts are associated to the decomposition, the partition of the y-axis Ci we chose. This is similar to the idea of the Riemann integral, but we immediately see that the decomposition of the x-axis below here is not connected. So we have different sets that are not connected in intervals as before. And this is the whole idea. Instead of choosing a fixed partition of the x-axis, we now choose a partition of the y-axis, of the values of the function. And then we get a useful partition of the x-axis that we can work with. Now the next question could be how to measure these lengths on the x-axis below. Therefore, on the domain of definition, which is here 3, but it could be some space, we need a so-called measure. We want to measure volumes in this space. This means that we want to measure the size of sets inside this space. So for example, if the space is R, we measure lengths. In R2 we would measure areas. In R3 it would be indeed we measure volumes of sets. But in abstract sense we always speak of volumes. Hence on the x-axis here we could choose a general measure space. We just have to know how to measure the size of sets or the volume of sets, and such a measure space is usually denoted by omega. This means in the end we will have an integral that works on all functions that are defined on some measure space omega. Indeed, this is all we need to define the integral. Now you see how we could define an upper sum in some sense. So we take the Ci here, and now I want the Ci to be this one. So maybe I do a little picture. So the Ci is this stripe here. So this would be an upper sum for the integral if we know the measure of the two sets together. Of course, these blue sets are just the pre-image of this interval under the function f. So maybe we just call it A. Now if I call the measure we have here in our measure space just by mu, then we can calculate this generalized rectangle. It is ci, so the height, times the length on the bottom. This is the measure of our set A. Now we have one part of the whole integral, and now we can do this for the whole partition. So we have a finite sum over I. Of course I should put an index I for A for the pre-image as well, and then we have a sum. And since we chose a finite partition of the y-axis, we have a finite sum here. And it is the upper sum or the lower sum, depending which ci we chose here. Then again, with some limit process with finite partitions, we will get the Lebesgue integral, and usually denoted by f d mu, since now it's depending on the measure we chose on the x-axis. Indeed, this construction now works for arbitrary measure spaces, since the x-axis doesn't need a partition anymore. We just need a partition of the axis that is R anyway. However, in this case, we really need the notion of a measure, even in one dimension. So here we know what the length of a subinterval is. It's just the difference between the right hand side and the left hand side. But here we need more. Or in other words, in the Riemann integral, we just measure lengths of intervals, but in the Lebesgue integral, we can have any fragmentation, and we have to know the measure of this fragmentation. But if we know how to measure any set in the real line, then we have a very robust integral definition. Well, this generalizes the Riemann integral and eliminates all problems we had in higher dimensions, since this measure theory works in every dimension as you want. You just have to know how to measure volumes. And also the dependence of the continuity is gone, since now we can measure the size of the set of the points of discontinuity. For example, if we have infinitely many points of discontinuity, but the measure of all these points, so the measure of the set of all the points is 0, we don't have a problem in the definition of the integral at all. And also for the last point, so these limit processes, we have good answers for. We will see that we have very good limit theorems that describe these limit processes for the Lebesgue integral. Even strong results for the one-dimensional case, but also in the general case of measure spaces. Okay, to sum it up, the Riemann integral is a classical notion. It may be easier to understand at the beginning level, but in the end, everyone wants to work with the Lebesgue integral. Thank you very much.